Proxima B. And
Yeah.
so what's the story? When are, and that it's Earth-like.
Yes. So what makes Proxima B interesting is that it's an Earth-like planet orbiting the nearest star to the sun.
If it goes as planned, the journey to Proxima B will take about 20 years. So realistically, it will be several decades before we can confirm if there is indeed life on that planet.
In an astonishing revelation, James Webb has made a breakthrough in exoplanet imaging, releasing the clearest and most detailed image of Proxima Centauri b, a potentially habitable exoplanet orbiting our nearest neighboring star, Proxima Centauri. This milestone marks a major advancement not only in our technological capabilities, but also in our quest to understand distant worlds that might harbor life. Join us as we dig deep into the unprecedented revelations of Proxima b and what it could mean for the future of exoplanet exploration. Let's start with some basics. Proxima Centauri is the nearest star system to Earth, at just 4.24 light-years away, and it's getting closer. Over the next few tens of thousands of years, it will come within 3.1 light-years of us. The first planet discovered around it, Proxima b, is it at the right distance from its star to potentially support liquid water on its surface. It's firmly within its star's habitable zone. Proxima b also has an estimated mass of 1.3 times our own world, which implies that it's only about 10% larger in diameter than Earth, and is almost definitely rocky. The hope and speculation is that it might have an Earth-like atmosphere, the same raw ingredients and elements as our world, and most excitingly, perhaps even life on the surface. However, the problem is, Proxima b is a lot closer to its parent star than Earth is to the Sun. Instead of 365 days, it takes a mere 11.2 days to orbit Proxima Centauri. Its average orbital distance is just 5% of the Earth-Sun distance at 7.5 million kilometers, which means that it's got to be tidally locked to its star by now, with one roasting side, one frozen side, and an intermediate ring that's probably the most temperate portion. It also means that the sun-facing side gets ravaged with these flares frequently and from a very close distance. These flares won't entirely strip an atmosphere away, but they will absolutely destroy any sort of UV-protecting ozone layer on timescales far faster than a planet could regenerate it. So Proxima b won't have an ozone layer, which means ultraviolet, ionizing radiation can reach the surface. Because it rotates at just 9% the speed of Earth due to its orbital period and its tidal locking, its magnetic field should be far weaker than ours is, offering reduced protection against charged particles and solar winds. As far as we can tell, the surface would be vastly irradiated by potentially deadly radiation from the sun, ionizing atoms and molecules on the light side, and potentially destroying any type of chemical-based life we could create. But those difficulties for human-like life might not pose any problems at all for the kind of life that would evolve on Proxima b. Anyways, depending on what's in the atmosphere and the water on the surface, life could be an absolute cinch on this world. Winds blow from the light, hot side to the cold, dark side, providing a solid means of energy transport. The lack of protection from ionizing radiation is troubling, until you realize that Proxima b itself emits extremely little ultraviolet light, owing to its low temperature. It's only during these flaring events, which occur approximately once every 2 to 3 months, that enough ultraviolet light is released to cause harm to the life it's exposed to. And it's true, even primitive UV-resistant life on the surface, like lichens or mosses, would be in trouble. But even a thin layer of protection would keep life safe. While the ozone layer won't do, there's another layer that would, in theory, perform wonderfully. The top 200 meters of an ocean. The ocean appears blue because water more readily absorbs longer wavelength, red light, than the shorter wavelength blues. Ultraviolet light is even shorter wavelength, and therefore penetrates the ocean the best. But marine life on Earth has already figured out the key adaptation, to take refuge in deeper waters when ultraviolet light is most intense. Given that these flares are clearly visible and the same side of the world always faces the sun, Either organisms could adapt to be UV resistant, or they could do what every terrestrial creature does, as appropriate, take shelter when danger comes. A cave, a dark place, or even deeper depths in open water would transform a potential catastrophe into a minor inconvenience. For red dwarf stars like Proxima Centauri, their worlds have conditions that make it unlikely for life to have taken the exact same evolutionary pathway that life on Earth took. But that doesn't spell doom for life. It merely indicates that alternative pathways are required to arrive at similar outcomes. Frequent flares and excessive blasts of ultraviolet radiation may spell doom if Earth-based life were subject to those conditions. But organisms that have adapted to their environments could survive these outbursts routinely. A few solar hiccups a year should pose no problem for life forms that developed under those exact, harsh conditions. After all, on every world, it should be the organisms most robust against the adversarial conditions they face that will survive. With this possibilities, Proxima b stands as a significant milestone in the search for habitable exoplanets and the potential for extraterrestrial life. And the James Webb Space Telescope is one of the main instruments that could play a crucial role in the search. The telescope, launched in December 2021, represents one of the most advanced tools available for examining celestial bodies like Proxima b. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet light spectra, James Webb is designed to operate predominantly in the infrared spectrum. This capability allows it to penetrate cosmic dust clouds that often obscure our view of distant objects, offering a clearer and more detailed examination of celestial phenomena. Infrared observation is particularly advantageous when studying exoplanets. For Proxima b, Webb's ability to detect infrared light enables it to capture crucial data about the planet's heat signatures and atmospheric composition, details that may be invisible to telescopes operating solely in the visible spectrum. Since its launch, James Webb has significantly advanced our understanding of Proxima b, providing insights that are both awe-inspiring and perplexing. One of the most groundbreaking revelations from the Webb telescope is the unprecedented clarity with which it has captured images of Proxima b. These images represent the sharpest view humanity has ever had of this intriguing exoplanet, revealing surface features that previous observations could not detect. For example, scientists are now able to observe a stark contrast between Proxima b's day side and night side, a significant advancement in our ability to analyze the planet's environmental conditions. The brighter appearance of the day side suggests the potential presence of reflective clouds or ice, raising intriguing questions about the planet's surface and atmospheric conditions. In contrast, the faint glows observed on the night side are a source of ongoing research and debate among astronomers. Initial hypotheses propose that this glow could be indicative of auroras, similar to the northern and southern lights seen on Earth. Given Proxima Centauri's status as a red dwarf star, known for its frequent and powerful solar flares, it is plausible that these flares interact with Proxima b's magnetic field, assuming the planet possesses one, to create this luminescent effect. This potential interaction implies the existence of an atmosphere that can effectively conduct solar wind particles, hinting at the possibility of Proxima b having a magnetic shield akin to Earth's. Such a shield would be vital for protecting the planet from harmful radiation, creating a more stable environment where life could potentially flourish. However, this is not the only explanation for the mysterious glow. Some researchers have suggested that it could be the result of volcanic activity, with active volcanoes on Proxima b potentially emitting light during the planet's nighttime. If this theory holds true, it could signify a geologically dynamic world with internal heat sources, potentially supporting subsurface life. Moreover, a more speculative theory posits that the glow could be artificial, possibly a signal from advanced alien technology. While this notion is not widely accepted within the scientific community and remains firmly in the realm of speculation, it highlights the range of possibilities that Proxima b presents. Each hypothesis, whether involving natural phenomena or intelligent design, fuels a deeper inquiry into the planet's potential for habitability. The reflective characteristics of Proxima b's day side, alongside the intriguing features noted in its nighttime observations, suggest conditions that could be conducive to life. For instance, if Proxima b has an atmosphere that effectively distributes heat, it might mitigate the extreme temperature fluctuations typically associated with tidal locking, a condition where one side of the planet constantly faces its star. This could create a temperate zone on the planet, increasing the chances of life-sustaining environments. Conversely, the threat posed by Proxima Centauri's frequent solar flares cannot be overlooked. These flares can bombard Proxima b with high levels of radiation, potentially stripping away its atmosphere over time and rendering the surface inhospitable. However, the presence of auroras or indications of a magnetic field suggested by the observed glow may point to a protective mechanism against such radiation. This duality raises compelling questions about the balance of conditions that could either support or hinder the possibility of life on Proxima b. The potential for volcanic activity adds another layer of complexity to the investigation of Proxima b. If active volcanoes exist, they could create environments reminiscent of Earth's hydrothermal vents, places where life thrives in complete darkness, deriving energy from the chemical processes occurring within the planet's interior. In this scenario, it is conceivable that life on Proxima b could exist not on the surface, but rather in subsurface habitats shielded from the harsh conditions of space. After all, the implications of the images captured by the James Webb Space Telescope are profound, not only because they provide new and exciting details about Proxima b, but also because they open up a plethora of questions. Is Proxima b truly a habitable world, or is it primarily a hostile environment, with only a few enticing clues hinting at the possibility of life? Could the enigmatic glow on its night side be a natural occurrence, or does it indicate something more extraordinary, perhaps even extraterrestrial in nature? Future observations conducted by James Webb will be critical in addressing these inquiries. The telescope's continued monitoring of Proxima b will focus on understanding its atmospheric composition, temperature variations, and potential biosignatures. This ongoing investigation promises to deepen our understanding of not only Proxima b, but also the broader search for life beyond our planet. But while James Webb has opened a new window into Proxima b, there are still limitations and challenges. For one, Proxima Centauri's activity remains a hurdle. Its frequent flares can disrupt observations and could also strip away Proxima b's atmosphere, complicating efforts to study it in detail. Additionally, because Proxima b is tidally locked, any atmosphere it has might differ significantly from Earth's in terms of circulation and stability. The other major challenge is distance. While 4.2 light-years may be close on an astronomical scale, it's still too far to send a probe in the near future. Observations by James Webb and other ground-based telescopes will remain our primary method of study for the foreseeable future. However, technological innovations are being explored to address these challenges. One of the most promising initiatives is the Breakthrough Starshot project, a collaborative endeavor backed by prominent scientists like Stephen Hawking and funded by billionaire philanthropist Yuri Milner. Breakthrough Starshot represents a transformative approach to space exploration. The primary goal of the project is to develop an entirely new class of space probes, small, lightweight nanoprobes equipped with light sails. These probes, while minuscule in size and mass, could achieve unprecedented speeds, potentially reaching up to 20% of the speed of light, or 0.2 c. If successful, these probes could make the journey to Proxima b, an exoplanet orbiting the star Proxima Centauri, just over 4 light-years from Earth, within 20 years of launch. This time frame would be a historic leap compared to any spacecraft launched to date, as even the fastest human-made object currently would take tens of thousands of years to reach Proxima b. The mechanics of breakthrough Starshot's light sail technology are fascinating. The idea centers around ultralight, wafer-sized probes attached to extremely thin and durable sails. These sails are designed to capture energy from highly focused laser beams directed from Earth. The laser beams would act as the primary propulsion system, allowing the probes to rapidly accelerate to a significant fraction of light speed. This laser-driven propulsion concept leverages recent breakthroughs in photonics, the science of generating and controlling photons, typically used in optical communications, and material sciences to solve the formidable challenges of interstellar travel. The laser beams needed for Breakthrough Starshot's mission would have to be immensely powerful, with an output potentially in the gigawatt range. For comparison, a gigawatt of energy is approximately equivalent to the output of a large nuclear power plant. This level of energy would enable the lasers to accelerate the tiny probes to their target speeds over just a few minutes. The lasers would likely need to be situated in a vast array, either on the ground, possibly in a remote desert location where interference is minimal, or even in space to reduce atmospheric distortion. Placing the lasers in space could provide a clearer path for the beams, but it would also introduce significant engineering challenges and costs. An essential aspect of Breakthrough Starshot is the development of the probe's light sails, which must be ultra-thin yet robust enough to endure the high-energy laser blasts without tearing or melting. While this technology is still in its conceptual phase, recent advancements in photonics and material science have made the idea more plausible. Engineers are exploring the potential of materials such as graphene and molybdenum disulfide, which are lightweight, flexible, and durable. Graphene, a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, is incredibly strong yet lightweight, making it a leading candidate for the construction of these sails. Another promising material, molybdenum disulfide, is similarly strong and offers unique properties that might help the sails withstand the extreme thermal and structural stresses of laser propulsion. These materials represent a new frontier in material science, combining minimal weight with remarkable strength and thermal resilience. While laser-driven light sails are suitable for unmanned probes, sending humans would require more substantial propulsion systems with energy sources that can last over long distances. This is why nuclear propulsion has been revisited, with both fission and fusion methods being considered viable for interstellar travel. Nuclear fission propulsion systems harness energy through the process of splitting atomic nuclei, releasing large amounts of energy. This method has already proven useful in both terrestrial and space applications, making it a likely candidate for further development in interplanetary missions within our solar system. In space exploration, fission reactors could provide a stable and continuous energy source for ion thrusters or other electric propulsion systems, allowing a spacecraft to generate steady and reliable thrust over extended periods. For instance, ion thrusters work by electrically charging particles, such as xenon ions, and accelerating them to high speeds to produce thrust. Powered by a nuclear fission reactor, such engines could provide consistent acceleration, allowing a spacecraft to gradually achieve high velocities over time, perfect for long-duration missions. NASA and other space agencies are already investigating the use of fission reactors to power space missions. A notable example is NASA's Kilopower project, which aims to create compact, lightweight nuclear reactors designed for space. While these systems were initially intended for use on Mars or other interplanetary destinations within our solar system, the same principles could be adapted to longer-duration, deep space missions. However, to make nuclear fission a feasible option for interstellar travel, several engineering and safety challenges must be addressed. Unlike relatively short interplanetary missions, A fission-based interstellar mission would require a reactor capable of operating autonomously for decades without refueling, potentially lasting throughout a multi-generational voyage to another star system. Additionally, the fission reactor would need to remain stable and reliable despite prolonged exposure to the radiation, micrometeorite impacts, and other challenges of deep space. Autonomy is crucial, as a spacecraft traveling beyond our solar system would face significant communication delays and be largely isolated from Earth. Therefore, engineers would need to design a fission reactor that could detect and respond to potential malfunctions, adjusting its operations without any human intervention. By creating a highly automated and resilient system, it might be possible to make nuclear fission propulsion a practical option for extended interstellar missions. While nuclear fission provides one potential pathway, nuclear fusion offers even greater promise, as it could theoretically propel a spacecraft to a significant fraction of the speed of light. Fusion, the process that powers stars like our Sun, involves combining atomic nuclei at high temperatures and pressures, releasing tremendous amounts of energy in the process. In terms of energy output, fusion far surpasses fission, meaning that it could accelerate a spacecraft to much higher speeds. If achieved, fusion propulsion could open up the possibility of reaching Proxima Centauri, the closest star system to the Sun, within a human lifetime. Achieving a controlled fusion reaction on Earth has proven to be a significant scientific and engineering challenge, let alone attempting to create and maintain such a reaction in space. Nonetheless, several exciting concepts for fusion propulsion have been proposed, each utilizing different methods to attempt sustained fusion. One such concept is the fusion-driven rocket, FDR, developed by researchers aiming to use magnetized target fusion to produce thrust. In this design, plasma is compressed until it reaches the necessary temperature and pressure to achieve fusion. The fusion reaction produces a high-energy exhaust that could propel the spacecraft at much faster speeds than chemical or ion propulsion systems. The fusion-driven rocket concept is promising because it addresses some of the difficulties of achieving fusion in space by using magnetic fields to contain and compress the plasma. The idea is that a series of carefully controlled fusion pulses would produce thrust, steadily accelerating the spacecraft to velocities much faster than conventional methods. Another noteworthy design, the Daedalus project, was developed by the British Interplanetary Society in the 1970s. This ambitious concept sought to propel an uncrewed spacecraft to the vicinity of a nearby star, such as Barnard's star, using nuclear fusion. The Daedalus design involved firing small pellets of deuterium and helium-3 fuel into a reaction chamber, where they would be ignited by an electron beam to create fusion. Each fusion reaction would produce a burst of high-speed particles, creating thrust that would push the spacecraft forward. Designed as a multi-stage system, Daedalus would burn through an enormous supply of fusion fuel in each stage, gradually accelerating to about 12% of the speed of light, potentially reaching its target star in just under 50 years. Despite the ingenuity of Daedalus, the concept remains largely theoretical, due to the technological hurdles that must be overcome before controlled fusion propulsion can become a reality. One major challenge is the need for a sustained, controlled fusion reaction in space. While experimental fusion reactors, such as the International Thermonuclear Experimental Reactor, are making progress on Earth, they require massive infrastructure and extremely high temperatures to sustain fusion. Creating a fusion propulsion system that can fit within the confines of a spacecraft and operate autonomously over decades is an enormous engineering feat. Furthermore, a fusion reactor for interstellar travel would require large amounts of helium-3, a rare isotope not found in abundance on Earth, but potentially available on the Moon or in the atmospheres of gas-giant planets like Jupiter and Saturn. If nuclear fusion isn't powerful enough, scientists have also been exploring antimatter propulsion. Antimatter, The mirror version of ordinary matter releases an incredible amount of energy when it comes into contact with matter, providing far more energy per kilogram than nuclear reactions. In simple terms, antimatter is composed of particles that have the same mass as their matter counterparts, but possess opposite charges. For instance, the antiparticle of an electron, known as a positron, carries a positive charge instead of a negative one. When antimatter comes into contact with regular matter, the result is a process called annihilation, where both particles are completely converted into energy. This reaction releases a staggering amount of energy, far exceeding what is produced by conventional chemical reactions and even surpassing the energy per kilogram produced by nuclear reactions. Because of this, scientists believe that antimatter could, in theory, provide the thrust needed to accelerate spacecraft to unprecedented speeds, possibly allowing travel close to 90% of the speed of light. The idea behind antimatter propulsion involves generating and storing antimatter, then carefully controlling its interactions with matter to produce a stream of high-energy particles. This high-energy release could, in turn, be harnessed to create thrust. An antimatter rocket would theoretically use the energy from matter-antimatter annihilations to drive high-velocity particles out of the back of the craft, propelling it forward at remarkable speeds. For instance, a gram of antimatter reacting with matter would release energy equivalent to an explosion of about 43 kilotons of TNT. At such a rate, even a tiny amount of antimatter would provide immense power, making it an ideal candidate for deep space missions where conventional fuel sources would be impractical. However, the prospect of antimatter propulsion comes with its own formidable challenges. The most pressing of these is the production and containment of antimatter. At present, antimatter can only be generated in extremely small quantities within particle accelerators. These massive machines can create antimatter by accelerating particles to high speeds and smashing them together, which occasionally results in the production of antimatter particles. While this process has proven that antimatter can indeed be created artificially, the quantities produced are minuscule, and the cost of production is prohibitively high. It's estimated that a single gram of antimatter could cost hundreds of billions of dollars to produce with current technology. This makes antimatter propulsion currently impractical for any large-scale application. Even if antimatter could be produced at a reasonable cost, storing it presents another considerable hurdle. Because antimatter annihilates upon contact with any matter, including the walls of any containment vessel, it cannot be stored in a regular physical container. Instead, scientists are investigating advanced containment methods using electromagnetic and magnetic fields. By creating a trap using magnetic fields, antimatter particles can be suspended in a vacuum, isolated from any contact with matter. This technology is still in its infancy, but progress is being made. One type of containment being explored is known as a penning trap, which uses a combination of electric and magnetic fields to confine charged particles. Future advancements in trap technology could make it possible to store antimatter safely for extended periods, potentially bringing antimatter propulsion a step closer to feasibility. If scientists are successful in overcoming these challenges, antimatter propulsion could open the door to remarkable advancements in space exploration. By enabling spacecraft to travel at a significant fraction of the speed of light, antimatter propulsion could make interstellar travel possible within human timescales. This means we might be able to send probes to distant star systems or even consider manned missions to nearby stars. Such advancements would have profound implications for humanity's understanding of the universe and could be the key to answering some of the biggest questions in astrophysics, such as the potential for life on exoplanets and the nature of distant celestial objects. In the coming decades, ongoing research in particle physics, advancements in particle accelerator technologies, and breakthroughs in containment methods may bring antimatter propulsion closer to reality. Although still a distant dream, scientists are optimistic that the incredible energy potential of antimatter could one day be harnessed for space travel. Should antimatter propulsion become feasible, it would represent one of the most groundbreaking achievements in human history, transforming the way we think about our place in the cosmos and potentially ushering in a new era of interstellar exploration. Another significant note: the distance and harshness of interstellar space require spacecraft to operate autonomously and with resilience against radiation and micrometeoroids. Thus, robotic probes equipped with AI and constructed using nanotechnology would be essential for a mission to Proxima b. AI would be critical for an interstellar mission, as communication delays make real-time control from Earth impractical. Probes and, eventually, crewed spacecraft would need onboard systems capable of autonomous decision-making for navigation, repairs, data collection, and even crisis management. NASA and private companies like SpaceX are investing heavily in AI for autonomous space systems, with developments in machine learning models capable of adapting to unforeseen circumstances in space. In addition, nanotechnology also could play a major role in reducing the mass and increasing the durability of interstellar probes. Lightweight materials made from carbon nanotubes and other nanostructures offer high strength-to-weight ratios, essential for light sail and other high-speed propulsion technologies. Nanomaterials also exhibit unique properties for radiation shielding, which would be crucial for both protecting sensitive electronics and ensuring the safety of human crews on such long journeys. Nanotechnology also supports the development of smart materials that can self-heal or adapt to damage from micrometeoroids or cosmic rays. Incorporating nanotechnology into spacecraft could reduce the need for redundant systems, making the vehicle lighter, more energy efficient, and better equipped for the journey to Proxima b. And for human missions, advanced life support systems are essential, considering that any journey would likely take decades even with the fastest propulsion systems. Current life support technologies on the International Space Station, also known as ISS, involve recycling water and oxygen, but interstellar travel demands innovations in closed-loop systems and biological support. NASA has been researching closed-loop life support systems that can recycle water, air, and waste with minimal resupply. Future systems might integrate algae or other forms of bioengineering to continuously replenish oxygen and food supplies. Bioregenerative systems, which mimic Earth's ecosystems, could offer a sustainable solution for interstellar travel, supporting human crews for extended periods without resupply from Earth. One of the ways to mitigate the challenges of long-duration space travel is to develop hibernation or cryogenic sleep technologies. Placing humans in a state of low metabolic activity could reduce the need for resources and prevent the psychological stresses of prolonged confinement. NASA has been exploring this concept for Mars missions, using techniques that reduce body temperature and metabolic rate. Although cryogenic sleep is still experimental, advances in medical technology and cryogenics could enable long-term hibernation for interstellar travelers, reducing life support requirements and making human missions to Proxima b more practical. Transmitting data back to Earth across interstellar distances is another major challenge. Traditional radio signals would become weaker over such long distances, so more advanced communication technologies are required. One promising solution is laser communication. Unlike radio waves, laser-based transmissions can achieve higher speeds and capacities, allowing for efficient data transfer across long distances. By directing a concentrated laser beam from an interstellar probe back to Earth, data can travel at significantly higher rates than with conventional radio signals. Organizations like NASA and ESA are already developing laser communication systems for deep space missions, and advancements in this technology could potentially support communication with probes traveling to distant exoplanets, such as Proxima b. Quantum communication represents another potential breakthrough in interstellar communication. This technology uses the phenomenon of quantum entanglement, which could theoretically enable instantaneous data transfer across vast distances. Though still in the early stages of development and not yet practical for interstellar use, research in quantum communication is progressing quickly. If these advancements continue, quantum communication could eventually provide real-time data transmission, opening new possibilities for communicating with interstellar probes or even crewed missions, significantly enhancing humanity's ability to explore deep space. Moreover, maintaining power for probes or crewed spacecraft over decades requires power sources that are both reliable and durable. Radioisotope thermoelectric generators, which convert heat from decaying radioactive material into electricity, have been used in space for decades, including on Voyager, Cassini, and the Mars rovers. For interstellar missions, radioisotope thermoelectric generators could be optimized with higher efficiency materials and longer-lasting isotopes, providing a steady power source for long-duration flights. On the other hand, if fusion technology becomes viable for propulsion, it could also serve as a sustainable power source for onboard systems, providing energy for life support, communication, and scientific equipment. Fusion reactors are still in development, but compact, sustainable reactors would be crucial for manned missions to Proxima b, as they offer energy density far exceeding current technologies. After all, sending probes and humans to Proxima b is one of the most challenging endeavors humanity could undertake. Although the technology required for such a journey does not yet exist, ongoing research in areas like light sail propulsion, nuclear fusion, antimatter propulsion, AI, nanotechnology, closed-loop life support, hibernation, and advanced communication shows promising potential. As these technologies develop, they may converge into an interstellar mission within the coming century. With breakthroughs in these fields, humanity may one day reach Proxima b, opening the door to exploring and perhaps even colonizing worlds beyond our solar system. The journey to Proxima b represents not only a technical challenge, but also a testament to human curiosity and our drive to explore the unknown.
The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang.
The universe has not existed forever. It was born. Around 1382 billion years ago, matter, energy, space, and time erupted into being in a fireball called the Big Bang. It expanded, and from the cooling debris, there congealed galaxies, islands of stars of which our Milky Way is one among about 2 trillion. This is the Big Bang theory. But the universe popping into existence out of nothing is so bonkers that scientists had to be dragged kicking and screaming to the idea. Even the physicist Brian Cox also said he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
A cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
Things got worse as James Webb, the most powerful space telescope, obtained some very strong evidence demonstrating that the Big Bang wasn't truly the start of it all. All begs the question, what happened before the Big Bang? And if the Big Bang wasn't the beginning, what was it? Join us as we shed some light on the origin of the universe. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of the theory's greatest detractors, Fred Hoyle, who was a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time, meaning that any observer not only anywhere but anywhen would perceive the universe to be in the same cosmic state. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science. But the idea, in its original form, wasn't simply that all of the universe's matter was created in one moment in the finite past. That notion, derided by Hoyle, had already evolved from its original meaning. Originally, the idea was that the universe itself, not just the matter within it, had emerged from a state of non-being in the finite past. And that idea, as wild as it sounds, was an inevitable but difficult to accept consequence of the new theory of gravity put forth by Einstein back in 1915, general relativity. When Einstein first cooked up the general theory of relativity, our conception of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way that gravitation worked was that any and all masses in the universe exerted a force on one another, instantaneously across space, in direct proportion to the product of their masses, and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was, or even what instantaneously meant with respect to two different locations. With the introduction of Einsteinian relativity, the notion that observers in different frames of reference would all have their own unique, equally valid perspectives on what distances between objects were and how the passage of time worked, it was only almost immediate that the previously absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe moved through this fabric, and the task for a novel theory of gravity would be to explain how not just masses, but all forms of energy shaped this fabric that underpinned the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this latter view, and, thinking the universe was static and eternal, added a special type of fudge factor into his equations, a cosmological constant. Although it was mathematically permissible to make this addition, the reason Einstein did so was because without one, the laws of general relativity would ensure that a universe that was uniformly distributed with matter, which ours seemed to be, would be unstable against gravitational collapse. In fact, it was very easy to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By introducing this extra term of a cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by proverbially pushing the universe out with an equal and opposing action. But two developments, one theoretical and one observational, would quickly change this early story that Einstein and others had told themselves. In the 1920s, Belgian physicist and Catholic priest Georges Lemaitre proposed a revolutionary idea, that the universe began as a primeval atom, which then expanded to form everything in existence. In 1927, Lemaitre published a paper proposing that the universe was expanding, a theory he based on Einstein's general relativity equations. Although his work initially received little attention, it became one of the key foundations for the Big Bang theory. Lemaitre's insights suggested a universe that had a specific starting point in time, radically challenging the static universe model. Around the same time, American astronomer Edwin Hubble made a groundbreaking discovery at the Mount Wilson Observatory in California. Observing distant galaxies, he noted a redshift in their light, meaning that the wavelengths of light from these galaxies were stretched, indicating that they were moving away from Earth. Hubble's work provided empirical evidence for the expansion of the universe, bolstering Lemaitre's theoretical predictions. In 1929, Hubble's law emerged, establishing a linear relationship between the distance of a galaxy and its velocity of recession, a key component supporting the Big Bang model. Fast forward to the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. The discovery of the cosmic microwave background and the subsequent measurement of its temperature and the black body nature of its spectrum eliminated alternative theories like the steady-state model. The measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis, while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. And the farther away we look in space, the less grown-up and evolved galaxies and stellar populations appear to be, while the largest scale structures like galaxy groups and clusters are less rich and abundant the farther back we look. The Big Bang, as verified by our observations, accurately and precisely describes the emergence of our universe as we see it, from a hot, dense, almost perfectly uniform early stage. But what about the beginning of time? What about the original idea of a singularity and an arbitrarily hot, dense state from which space and time themselves could have first emerged? That's a different conversation today than it was back in the 1970s and earlier. Back then, we knew that we could extrapolate the hot Big Bang back in time, back to the first fraction of a second of the observable universe's history. Between what we could learn from particle colliders and what we could observe in the deepest depths of space, we had lots of evidence that this picture accurately described our universe. But at the absolute earliest times, this picture breaks down. There was a new idea, proposed and developed in the 1980s, known as cosmological inflation, that made a slew of predictions that contrasted with those that arose from the idea of a singularity at the start of the hot Big Bang. In particular, inflation predicted a curvature for the universe that was indistinguishable from flat, to the level of between 99.99% and 99.9999%. Comparably, a singularly hot universe made no prediction at all. Equal temperatures and properties for the universe, even in causally disconnected regions. A universe with a singular beginning made no such prediction. A universe devoid of exotic high-energy relics like magnetic monopoles. An arbitrarily hot universe would possess them. A universe seeded with small magnitude fluctuations that were almost, but not perfectly, scale invariant. A non-inflationary universe produces large magnitude fluctuations that conflict with observations. A universe where 100% of the fluctuations are adiabatic and 0% are isocurvature. A non-inflationary universe has no preference. A universe with fluctuations on scales larger than the cosmic horizon. A universe originating solely from a hot Big Bang cannot have them. And a universe that reached a finite maximum temperature that's well below the Planck scale, as opposed to one whose maximum temperature reached all the way up to that energy scale. The first three were post-dictions of inflation. The latter four were predictions that had not yet been observed when they were made. On all of these accounts, the inflationary picture has succeeded in ways that the hot Big Bang, without inflation, has not. During inflation, the universe must have been devoid of matter and radiation and instead contained some sort of energy, whether inherent to space or as part of a field, that didn't dilute as the universe expanded. This means that inflationary expansion, unlike matter and radiation, didn't follow a power law that leads back to a singularity, but rather is exponential in character. One of the fascinating aspects about this is that something that increases exponentially, even if you extrapolate it back to arbitrarily early times, even to a time where TE, it never reaches a singular beginning. Now, there are many reasons to believe that the inflationary state wasn't one that was eternal to the past, that there might have been a pre-inflationary state that gave rise to inflation, and that, whatever that pre-inflationary state was, perhaps it did have a beginning. There are theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open, and this remains an active and exciting area of research. But one thing is for certain, whether there was a singular ultimate beginning to all of existence or not, it no longer has anything to do with the hot Big Bang that describes our universe from the moment that inflation ended. The hot Big Bang occurred. The universe became filled with matter and radiation and more, and it began expanding, cooling, and gravitating, eventually leading to the present day. There are still a minority of astronomers, astrophysicists, and cosmologists who use the Big Bang to refer to this theorized beginning and emergence of time and space. But not only is that not a foregone conclusion anymore, but it doesn't have anything to do with the hot Big Bang that gave rise to our universe. The original definition of the Big Bang has now changed, just as our understanding of the universe has changed. If you're still behind, that's okay. The best time to catch up is always right now. Because James Webb, the supreme observatory that was built to revolutionize our understanding of the universe, is providing more and more evidence that the Big Bang wasn't really the beginning of it all. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover details of cosmic dawn never before observed. Since it first started sending back science data in mid-2022, the internationally funded state-of-the-art telescope has been giving us images of distant galaxies that appear to have formed and matured far earlier than our models predicted. Webb's haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with the dozens found so far. It's enough of a problem that some are calling it a challenge to our entire cosmic timeline. According to the standard model of cosmology, after the fiery Big Bang 13.8 billion years ago, the universe cooled, and energy turned into matter that eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process. But Webb's results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines then, break the universe, and upend models of cosmic history. Subsequent data have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. According to Priyamvada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut, no data at the moment has broken the universe, but I think there are interesting potential tensions emerging on different scales. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution. That could mean bringing new ideas to the forefront, while leaving others in the cosmic dustbin. Prior to the launch of James Webb, no one knew if galaxies could even form so early in the universe's 13.8 billion year history, at a time when matter was thought to still be sedately coalescing into the gravitationally bound clumps required to give birth to large groups of stars. As Garth Illingworth, an astronomer at the University of California, Santa Cruz, said at a press conference held by NASA to announce the peer-reviewed validation of the first two candidates. And so we're wondering, do we really understand the early phases of the formation of these galaxies? This has posed a lot of questions for the theorists. Chief among them is how exactly dark matter guided the emergence of galaxies. For the first few 100,000 years after the Big Bang, the cosmos was so hot that gravity could not pull normal matter together to form large protogalactic clumps. But this was not an issue for dark matter, says Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, because dark matter does not interact via electromagnetic forces. Instead, gravity alone is this invisible substance's master, meaning that in mere moments after the Big Bang, when primordial chaos otherwise reigned, gravity immediately began glomming together dark matter into large clumps known as halos. These dark matter halos are believed to have acted as gravitational sinks for normal matter, seeding the subsequent formation of galaxies in the early universe. The telltale motions of the stars they shepherd betray their endurance to this day. Such halos still surround galaxies like our own, majestic but invisible sculptors of the modern cosmos. James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structure. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. However, perhaps instead these halos were simply more efficient at drawing in regular matter to feed star formation. Today our galaxy produces roughly 1 new star per year, but Castellano's paper suggests that star formation rates must have been at least 20 times higher in his and Naidu's 2 candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just at 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, such outsized rates of star formation stretch the boundaries of what is physically possible. In the words of Boylan Colchin, if those values are correct, you'd need to have our galaxies turning all their mass into stars and forming stars as fast as they could. Researchers have likened the impossible early galaxy problem to flipping through someone's old photo album, expecting to find baby pictures, and seeing a full-grown adult instead. With a person, you might just conclude that they're older than you thought, but with early galaxies, you very quickly run into a problem with the age of the universe itself. For generations, people argued over whether the universe had always existed, whether it had a beginning, or whether it was cyclical, with neither a beginning nor an end. But starting in the 20th and continuing into the 21st century, we not only drew a scientific conclusion to that question, the universe, as we recognize it, began with a hot Big Bang, but we were able to pinpoint precisely when that beginning occurred. The simplest and most straightforward way to measure the age of the universe is simply to look at the objects that are in it. Stars, for instance. We have hundreds of billions of stars in the Milky Way galaxy alone, and the overwhelming majority of the ancient history of astronomy was devoted to studying and characterizing stars. It remains an active field of research today, as astronomers have uncovered the relationship between observed properties of stellar populations and how old they are. The basic picture is that a cloud of cold gas collapses under its own gravity, leading to the formation of large numbers of new stars all at once that come in all different masses, colors, and brightnesses, and the largest, bluest, brightest stars burn through their fuel first. Therefore, when we look at a population of stars, we can tell how old it is by looking at what types stars still remain and what classes of stars are completely gone. Our galaxy has stars of all different ages in it, but the measurements of any individual star will be riddled with uncertainties. The reason is simple. When we view an individual star, we see it as it is today. We cannot see or know what happened in that star's past history that may have led to its present condition. We can only view a present-day snapshot of what exists and have to infer the rest. You'll often see attempts made to measure the age of an individual star, but that always comes along with an assumption that the star didn't have an interaction, merger, or other violent event in its past. Because of that possibility, and the fact that we only see the survivors when we look at the universe today, those ages always come along with massive uncertainties, on the order of 1 billion years or even more. However, the uncertainties are much smaller when we look at large collections of stars. The collections of stars that form within a galaxy like the Milky Way, open star clusters, typically contain a few thousand stars and only last a few 100 million years. The gravitational interactions between these stars eventually cause them to fly apart. While a small percentage last 1 billion years or even a few billion years, we have no known open star clusters that are even as old as our own solar system. However, globular clusters are larger, more massive, and more isolated, found throughout the halo of the Milky Way and most large galaxies. When we observe them, we can measure the colors and brightnesses of many of the stars inside, enabling us, so long as we understand how stars work and evolve, to determine the ages of these star clusters. Although there are uncertainties here as well, there is a large population of globular clusters, even within the Milky Way alone, with ages of 12 billion years or more. How certain are we of these figures? It's tough to say. While it's almost guaranteed that the oldest of these star clusters must be between 12.5 and 13 billion years old, there remain large uncertainties about the amount of time required for a star right around the mass of our Sun to begin its transition into a subgiant, followed by its transformation into a full-blown red giant star. It could be 10 billion years, it could be 12 billion years, it could be some value in between. For years, many astronomers who worked on globular clusters argued that the oldest ones were 14, maybe even 16 billion years old. But a shift in our understanding of stellar evolution now disfavors that interpretation of the data. Today, we can reliably conclude there's a lower limit to the age of the universe of around 12.5 to 13 billion years from the stars we measure. But that doesn't pin down the age precisely. It's a good constraint to have, but to arrive at an actual figure, we'd like a better method. Fortunately, the universe gives us one. You see, Einstein's general relativity, for a universe filled with even amounts of matter and energy everywhere and in all directions, gives a straightforward relationship between two quantities: the amounts and types of matter and energy present within the universe, and how fast the universe is expanding today. This relationship was first derived all the way back in 1922 by Alexander Friedmann, and the equations that enable us to derive how old the universe must be are known as the Friedmann equations. It took us many years to measure the constituents of the universe, but a consensus picture has emerged. Observations ranging from the abundances of the light elements to the clustering of galaxies to how galaxy clusters collide to distant supernovae to the fluctuations in the cosmic microwave background all point toward the same universe. In particular, it's made up of 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos, 0.01% photons, and less than 0.4% of everything else, including spatial curvature, cosmic strings, domain walls, and other fanciful, exotic components. This picture agrees with the full suite of observations that we have. You have to really cherry-pick your evidence very hard, overemphasizing measurements with large ambiguities while simultaneously ignoring large suites of data, to wind up with sets of values that vary significantly from this. So then, you might think that everything hinges on the expansion rate. If you can accurately measure that, you can simply do the math and precisely arrive at the age of the universe. Beginning the early 2000s and ever since, the best data we have comes from the cosmic microwave background, first from WMAP, then from Planck, and as of July 14, 2020, from the Atacama Cosmology Telescope as well. Those values have all converged on the same expansion rate, 68 kilometers SSMPC, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, you get a very robust 13.8 billion years, completely consistent with everything we know about stars. Hang on a second, though. You might have heard, and rightly so, that there's a controversy over this. While teams using the cosmic microwave background might all obtain one value for the expansion rate, and teams measuring the large-scale structure of the universe might agree, other methods yield a wildly different value. The other methods, rather than beginning with an early imprinted signal and measuring how it appears today, begin close by and work outward. They measure distances and the apparent recession speeds of various objects, a method generally known as the cosmic distance ladder. When you look at the distance ladder measurements, they all appear to give systematically higher values, between 72 and 76 kilometers SSMPC, about 9% higher on average than the value you get from the cosmic microwave background. You might think then that someone's right and someone's wrong. If the distance ladder team is correct and the cosmic microwave background team is wrong, then perhaps the universe is 9% younger than we think, just 12.8 billion years old. But that's not how it works in practice. The data from the cosmic microwave background isn't something that can just be ignored. It's something that must be reckoned with. The peaks, valleys, and wiggles that we see in its temperature fluctuations are a reflection of all these different parameters combined. Sure, the best fit values are for a universe expanding at 68 kilometers SSMPC and with 68% dark energy, 27% dark matter, and 5% normal matter, but those can be varied, so long as they all vary together. Although it doesn't fit the data quite as well, you can up the expansion rate to, say, 74 kilometers s/mpc, and still arrive at a very good fit, so long as you're willing to change the relative fractions of dark matter and dark energy. With a little less dark matter, 20%, and a little more dark energy, 75%, a substantially higher expansion rate can still fit the data well, although not quite as well, as the consensus values. However, what's fascinating about this is that the derived age barely changes at all. If you explore the full range of what is and isn't allowed, that 13.8 billion-year-old figure only comes along with an uncertainty of about 1%, between 13.67 and 13.95 billion years. But it's true that there are still many mysteries left to be uncovered about the universe. We don't know how fast the universe is expanding, and we don't know why different methods of measuring the expansion rate give such wildly different results. We don't know what dark matter or dark energy are, or whether general relativity, from which all this is derived, is still valid on the largest of cosmic scales. We don't even know exactly how much of the universe is locked up in which form of energy. It could have more dark matter and less dark energy than we think, or vice versa. The uncertainties are substantial. Similarly, we know that the universe is approximately 13.8 billion years old, but its exact age is not yet clear. Even today, the matter remains open to discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. That's what happened recently, when a new study based on James Webb's data was released, challenging the long-held notion that our universe is nearly 13.8 billion years old. If the findings of this latest research prove accurate, the Big Bang may have taken place 26.7 billion years ago, making the actual age of the universe nearly twice as old as we thought. According to Rajendra Gupta, a theoretical physicist at the University of Ottawa who authored the study, with the new model, we can explain the conundrum that has long puzzled scientists about these ancient galaxies. That's because Gupta's newly devised model stretches the galaxy formation time by a several billion years. This age estimate is derived from the universe's expansion rate by measuring the redshift of spectral lines in the light emitted by distant galaxies. The redshift of light is what has long helped to inform physicists' estimates of the universe's age. In simple terms, the thought has been that the redshift indicated the distance of stars and galaxies, and hence, the faster they are moving away from Earth. By estimating the rate at which the stars are moving away, scientists can calculate how fast space is expanding into an infinitely growing universe. But the so-called tired light theory that originated in 1929 with Swiss astronomer Fritz Zwicky offered an alternative explanation. Perhaps the redshift we see isn't due to galaxies moving away from us. Instead, Zwicky's hypothesis was that it might be because light loses its energy and shine after traveling a long distance. Gupta proposes that if we allow Zwicky's theory to coexist with the idea of an expanding universe, we can reinterpret the redshift as a hybrid of both of these phenomena and thus arrive at an even more accurate age estimate of the universe. And Gupta goes even further in the study, introducing the fundamental physics idea from English theoretical physicist Paul Dirac, that coupling constants govern the interactions between particles. What does that mean? If these constants evolve, then the time it takes for the early galaxies observed in the Webb telescope to form extends from a few 100 million years to several billion years. Better put, it would offer an explanation for the advanced level of development and mass observed in the previously puzzling early galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
The entire universe will be aware of this one explosion.
It's a star also that is on the verge of death.
In the vast expanse of the cosmos, few stars capture the imagination of both scientists and enthusiasts as much as Betelgeuse. Known as the shoulder of the constellation Orion, this massive red supergiant has always intrigued astronomers, particularly due to its size, brightness, and potential for a supernova event in the relatively near future. In recent times, Betelgeuse has once again made headlines, this time because of a startling increase in brightness, an unprecedented 250% rise in luminosity, detected by the James Webb Space Telescope. This unexpected and dramatic surge has reignited discussions about the fate of this star. What would happen if Betelgeuse exploded tomorrow? What kind of cosmic fireworks would we witness? How would the explosion affect Earth, both in terms of direct impacts and the cultural ramifications? And finally, what would be the long-term consequences for our understanding of the universe? All this and more will be discussed in today's episode. Located approximately 700 light-years away from Earth, Betelgeuse is one of the brightest stars visible from Earth. It is classified as a red supergiant, meaning it is a star in the late stages of stellar evolution. One of Betelgeuse's most striking characteristics is its sheer size. It is about 900 times the size of our Sun, and if placed at the center of our solar system, would extend beyond the orbit of Jupiter. This makes Betelgeuse one of the largest stars known, though its mass is more modest, about 15 to 20 times that of the Sun. However, despite its massiveness, Betelgeuse is not destined to live long. Stars of this size burn through their fuel quickly and are expected to live only a few million years compared to the Sun, which has a lifespan of around 10 billion years. Betelgeuse itself is a stellar heavyweight that has already burned through much of its hydrogen fuel and is now fusing heavier elements like helium, carbon, and oxygen in its core. This is a common process for massive stars, where they go through a series of stages in which different elements are fused to produce energy. However, as heavier elements are fused, the process becomes less efficient, leading to instabilities in the star's outer layers. These instabilities are evident in the star's variability in brightness. Betelgeuse is known as a semi-regular variable star, meaning its brightness fluctuates over time. Sometimes it can shine as the 9th brightest star in the sky, and other times it dims significantly. The causes of this variability are complex and are believed to be related to pulsations in the star's outer layers, where massive convective cells rise and fall, much like boiling water in a pot. These fluctuations contribute to the star's bloated appearance, which can change dramatically over time. And according to Estimat, Betelgeuse typically has a 400-day cycle, as well as a longer cycle that stretches about 5 years. But in 2019, something strange happened. In the fall of 2019, Betelgeuse started to drastically dip in brightness, outside of its typical brightening and fading cycle. Within months, the star had dimmed by about 60% in an event now known as the Great Dimming. This sudden dimming was so significant that some scientists wondered if Betelgeuse was entering a pre-supernova phase, which precludes a massive star's explosive death in a supernova. Talk of a possible explosion sparked intrigue around the world, as Betelgeuse would be the closest supernova to ever be observed and recorded by humans. By April of 2020, Betelgeuse had returned to its normal brightness, but the dimming remained a mystery. There were early attempts to make sense of the strange and unusual event, but the full picture wouldn't be revealed until the next year. By analyzing data from observatories, including NASA's Hubble Space Telescope, scientists found that Betelgeuse blew its top in 2019. The star spewed a giant piece of its surface material out into space, which is a type of event known as a surface mass ejection. Once in space, this material cooled into a dust cloud that temporarily blocked the light from the star. Ejecting material is fairly normal for stars. In fact, our Sun does this routinely, blowing out material from its outer atmosphere, or corona, in events called coronal mass ejections. But the Betelgeuse eruption was not like the Sun's routine ejections. Betelgeuse blew 400 billion times as much mass as is usually emitted during a coronal mass ejection, and the chunk it spewed out into space likely weighed several times as much as our moon. Scientists think that the massive, never-before-seen ejection was potentially caused by a plume of gas bubbling up from within the star, which was assisted by the star's normal 400-day pulsation cycle. The cause of the event was later traced to an enormous expulsion of material from the star's interior that created a huge dust cloud that subsequently obscured our view of the star. However, it is worth noting that although the dust cloud has since dissipated and Betelgeuse has regained its usual brightness, the star has not been quite its old self since. Its 400-day brightness oscillation period has halved to 200 days, and on top of that, in recent days, the star began to brighten beyond its usual peak luminosity. The sudden increase in brightness raises the question of what exactly is causing this unusual event. Several theories have emerged, each suggesting a different possibility for what is happening inside Betelgeuse. One possibility is that the increase in brightness is due to extreme pulsations within Betelgeuse. As a red supergiant, Betelgeuse experiences periodic pulsations where its outer layers expand and contract. These pulsations can lead to fluctuations in brightness, but a 250% increase is far more dramatic than the usual cycles observed in the past. Some astronomers speculate that these pulsations may be growing in intensity as the star approaches the end of its life, potentially signaling that it is entering a more volatile phase. Another possibility is that the increased brightness is caused by changes in Betelgeuse's convection cells. Like all stars, Betelgeuse is constantly churning with hot plasma that rises from the star's core to its surface, cools, and then sinks back down. These convection currents create enormous cells, some of which can be as large as the star itself. If one of these convection cells has grown unusually large or undergone a significant change, it could lead to a temporary but substantial increase in brightness. This could explain why Betelgeuse suddenly appears much brighter than before. However, this is still a speculative theory, and more data is needed to determine whether convection is responsible for the observed changes. The most exciting possibility is that Betelgeuse is on the verge of going supernova. When a massive star like Betelgeuse finally runs out of fuel, its core will collapse, triggering one of the most violent events in the universe, a Type II supernova. This collapse happens because the star's nuclear fusion process, which converts hydrogen into heavier elements, will no longer be able to counteract the force of gravity. Without the outward pressure from fusion, Betelgeuse will implode. This collapse will cause an extraordinary release of energy. Within moments, Betelgeuse's outer layers will be blasted into space at speeds of thousands of kilometers per second. The explosion will produce a blinding light, a flash that could briefly outshine the entire Milky Way galaxy. For several weeks or months, Betelgeuse will become the brightest object in the night sky, easily visible even during the day. Thus, one of the most immediate and spectacular consequences of a Betelgeuse supernova would be its appearance in Earth's sky. Depending on the exact mechanics of the explosion, Betelgeuse could shine as bright as the full moon. Imagine stepping outside at night and seeing not only the moon, but also an additional luminous point of light in the sky. Even during the day, the supernova might be visible, its brightness rivaling that of Venus, the brightest planet in our night sky. For stargazers and scientists alike, this event would be a once-in-a-lifetime cosmic display. The constellations would be altered temporarily, as Orion's shoulder, the position Betelgeuse occupies, would no longer look like it had before. This alteration could last for years as the light from the explosion dims and the material blown off in the explosion forms a nebula. While the visual spectacle would be breathtaking, some might wonder whether Betelgeuse's explosion could pose a danger to Earth. Thankfully, despite its relatively close distance of 640 light-years, We are far enough away that Earth would be safe from most of the hazardous effects of a supernova. The main danger from a supernova comes in the form of radiation, particularly gamma rays. However, most scientists believe that a supernova would need to occur within 25 to 50 light-years of Earth to pose a serious threat to our planet's biosphere. At 640 light-years away, Betelgeuse is far outside the danger zone. That said, Earth would still receive an influx of radiation in the form of high-energy particles and cosmic rays, but the effects would be minimal. Our atmosphere and magnetic field would shield us from most of this radiation. Satellites and space missions could be more vulnerable to these energetic particles, but the overall impact on life on Earth would be negligible. Regardless, one thing is for sure: if Betelgeuse exploded tomorrow, it would undoubtedly have a profound cultural impact on humanity. Throughout history, supernovae have been seen as omens, strange lights in the sky signaling great events or upheavals. For example, Chinese astronomers recorded the supernova that created the Crab Nebula in 1054, and it became a key part of their historical astronomical records. Some modern interpretations suggest that supernovae recorded by ancient civilizations may have been integrated into their mythologies. In today's world, where the mystery of the cosmos is tempered by scientific understanding, an exploding star would likely inspire awe more than fear. News of the supernova would dominate headlines, with social media flooded with images and updates from astronomers. People all over the world would step outside to witness this rare cosmic event, perhaps sparking renewed interest in astronomy and the mysteries of the universe. Religions, astrologers, and spiritual communities might interpret the event in diverse ways. Some could see it as a divine sign, while others might use it as a symbol of change, transformation, or the fragility of existence. The idea that we are witnessing the death of a star that has been a fixture in our sky for millennia might stir existential reflections on humanity's place in the universe. For astronomers and astrophysicists, the explosion of Betelgeuse would offer an unprecedented opportunity to study a nearby supernova in real time. We've observed supernovae in distant galaxies, but a supernova as close as Betelgeuse would allow for much more detailed data collection. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories around the world would turn their attention to Betelgeuse immediately. Scientists would study the light curve of the explosion, the energy spectrum emitted, and the interaction between the shockwave and the surrounding material. This data could help refine our models of how supernovae work, improving our understanding of stellar life cycles and the formation of neutron stars or black holes. In particular, scientists would be keen to see whether Betelgeuse leaves behind a neutron star or collapses further into a black hole. The exact conditions that lead to one outcome versus the other are still not fully understood, and Betelgeuse's explosion could provide crucial insights. Besides, Betelgeuse's explosion might also have long-term implications for space exploration. The debris from the supernova would expand outward, creating a shockwave that could sweep through nearby regions of space. While this shockwave would take thousands of years to reach us, it could eventually pass through areas of interest for future space missions. More immediately, Betelgeuse's explosion would give scientists valuable data about how stars die and how their remnants, neutron stars and black holes, behave. This could inform future missions aimed at studying these extreme objects. For instance, if Betelgeuse collapses into a neutron star, we might send probes to study the pulsar it becomes, providing an opportunity to test theories about the behavior of matter under extreme gravitational and magnetic forces. In addition, a supernova explosion like Betelgeuse's reminds us of the dynamic, ever-changing nature of the universe. While stars appear to us as fixed points of light, they are living entities with life cycles of birth, growth, and death. Betelgeuse's explosion would be a vivid demonstration of this reality. On a larger scale, supernovae play a crucial role in the evolution of galaxies. They are responsible for distributing heavy elements like iron, gold, and uranium into space, elements that make up planets and life itself. Betelgeuse's explosion would contribute to this ongoing process, helping to recycle stellar material for future generations of stars. In short, if Betelgeuse exploded tomorrow, humanity would be treated to a once-in-a-lifetime spectacle. While the explosion would be a breathtaking visual event, its scientific, cultural, and philosophical impacts would resonate for generations. We would have a front-row seat to one of the most powerful events in the universe, and it would deepen our understanding of the cosmos. In the end, Betelgeuse's explosion would serve as a reminder of the immense forces at work in the universe and our small yet significant place within it. However, it is worth noting that despite Betelgeuse's popularity, there are several other stars in our galaxy that may be better candidates for the next supernova, based on factors such as mass, age, and location within the Milky Way. Here are 5 better candidates than Betelgeuse for our galaxy's next supernova. 1. Eta Carinae. Eta Carinae is one of the most massive stars in our galaxy, located around 7,500 light-years away in the Carina constellation. It belongs to a system of 2 stars, with the primary star being a hypergiant that is 100 to 150 times the mass of the Sun. This star is on the brink of explosion, making it one of the top candidates for the next supernova. Eta Carinae has already shown signs of instability. In the 19th century, it experienced a massive outburst known as the Great Eruption, during which it briefly became the second brightest star in the night sky. This outburst ejected a huge amount of material into space, forming the Homunculus Nebula, a distinctive cloud of gas and dust that surrounds the star today. The massive size of Eta Carinae means that its core is undergoing rapid nuclear fusion, and it is burning through its fuel at an extraordinary rate. As it nears the end of its life, the star is likely to undergo core collapse, leading to a Type II supernova. Given its history of instability and massive size, astronomers believe that Eta Carinae could explode within the next few 100,000 years, making it a prime candidate for our galaxy's next supernova. When Eta Carinae does go supernova, it will be an extraordinary event. The explosion could be visible from Earth even during the daytime, and it could potentially create a gamma-ray burst, one of the most energetic events in the universe. The massive size of Eta Carinae means that its supernova could be much more powerful than typical stellar explosions, leaving behind either a black hole or a neutron star. 2. WR-104. WR-104 is a binary star system located about 7,500 light-years away in the constellation Sagittarius. It consists of a Wolf-Rayet star and an O-type companion star. Wolf-Rayet stars are known for their extreme temperatures and mass loss, and they are often considered precursors to supernovae. WR-104 is already in the late stages of its life. The Wolf-Rayet star in the system is shedding massive amounts of material as it burns through its nuclear fuel. This process is a clear indicator that the star is nearing the end of its life and will likely go supernova in the near future. What makes WR-104 particularly interesting is the fact that it is pointed almost directly at Earth. Some astronomers have raised concerns that when WR-104 goes supernova, it could produce a gamma-ray burst that would be directed toward our planet. While the likelihood of this happening is relatively low, it adds an extra layer of intrigue to WR-104's potential supernova. If WR-104 were to produce a gamma-ray burst directed at Earth, the effects could be devastating. Gamma-ray bursts are incredibly energetic and could potentially strip away Earth's ozone layer, exposing the planet to harmful radiation from the sun. However, even without a gamma-ray burst, the supernova would be an extraordinary event, lighting up the night sky and leaving behind a neutron star or black hole. 3. V Canis Majoris. VY Canis Majoris is a red hypergiant located around 3,900 light-years away in the constellation Canis Major. It is one of the largest known stars in the universe, with a radius approximately 1,420 times that of the Sun. Its immense size and advanced age make it a prime candidate for a supernova in the near future. Like Betelgeuse, VY Canis Majoris is a red supergiant that is nearing the end of its life. However, VY Canis Majoris is much larger than Betelgeuse, and its advanced age means that it could go supernova sooner rather than later. The star is already experiencing significant mass loss, a key indicator that it is in the late stages of its life. VY Canis Majoris is so large that it could end its life in a hypernova, an exceptionally powerful type of supernova that occurs when extremely massive stars collapse. This type of explosion would release an enormous amount of energy and could create a black hole. If VY Canis Majoris were to go supernova, it would be a spectacular event. The explosion could be visible from Earth even during the daytime, and it would release an immense amount of energy. The aftermath of the explosion could leave behind a black hole, adding to the growing number of black holes in our galaxy. 4. Betelgeuse's sister star, Mu Cephei. Mu Cephei, also known as the Garnet Star, due to its deep red color, is another red supergiant located about 5,000 light-years away in the constellation Cepheus. It is slightly larger than Betelgeuse, with a radius around 1,750 times that of the Sun. Like Betelgeuse, Mu Cephei is nearing the end of its life and could go supernova in the near future. Mu Cephei shares many characteristics with Betelgeuse, including its advanced age and red supergiant status. However, Mu Cephei is slightly larger and may be further along in its evolutionary process, making it a better candidate for the next supernova. The star is currently shedding large amounts of material, a key indicator that it is in the late stages of its life. As Mu Cephei continues to burn through its nuclear fuel, it will eventually undergo core collapse, leading to a Type II supernova. If Mu Cephei were to go supernova, it would be a stunning event. The explosion could be visible from Earth, even without the aid of telescopes. Given its large size, the supernova could leave behind either a neutron star or a black hole. While the distance of Mu Cephei from Earth means that its explosion would not pose a direct threat to our planet, it would still be a remarkable cosmic event. 5. RS Ophiuchi. RS Ophiuchi is a recurrent nova system located around 5,000 light-years away in the constellation Ophiuchus. It consists of a white dwarf and a red giant star in a close binary system. The white dwarf accretes material from the red giant, leading to periodic nova outbursts. RS Ophiuchi is a unique candidate for a supernova because it is part of a binary system. The white dwarf in the system is gradually accumulating material from its companion star, and as it approaches the Chandrasekhar limit, the maximum mass a white dwarf can have before collapsing, it is likely to undergo a Type Ia supernova. Type Ia supernova are different from the core collapse supernovae that occur in massive stars like Eta Carinae and VY Canis Majoris. Instead, they occur when a white dwarf in a binary system accretes enough material to trigger a runaway nuclear reaction. RS Ophiuchi has already undergone several nova outbursts, and astronomers believe that it could eventually go supernova. A Type Ia supernova from RS Ophiuchi would be an incredible event. These explosions are incredibly bright and are often used as standard candles to measure distances in the universe. The explosion would release a tremendous amount of energy, and the remnants could include a neutron star or black hole. While the distance of RS Ophiuchi from Earth means that its supernova would not pose a direct threat, it would still be a spectacular event for astronomers to observe. In the meantime, let's take a quick look at some recent remarkable space discoveries. Just days ago, researchers had observed the first ever confirmed solar flare, an intense burst of radiation emitted from the sun. It was a warning something big was about to hit our planet. Most of the northern and southern skies lit up with brilliant auroras, signaling that a massive solar storm was underway. This storm, later named the Carrington event, was one of the strongest in documented history. However, in a recent article in Nature, we have shown that in the not-so-distant past, the Earth was battered by much more extreme solar storms. Evidence of these storms has come, in particular, from analyzing levels of radioactive carbon, known as radiocarbon or carbon-14, in tree rings. Solar storms cause disturbances in the Earth's magnetic shield or magnetosphere. One frequent way they are caused is by coronal mass ejections, outpourings of charged particles from the sun, that make their way to Earth and penetrate the magnetosphere. Extreme solar storms could spell disaster for our highly technological society because they have the potential to damage satellites and bring down communications networks and global electricity grids. The strength of some past extreme solar storms detected in tree rings suggest they would have played havoc with our technological infrastructure on a scale never seen before. One extreme solar storm known to have occurred in AD 774, for example, would have dwarfed the Carrington event. Radiocarbon, or carbon dating, has been widely used for decades to age objects that were once alive, such as bone, wood, and leather. When plants and animals die, the radiocarbon inside them decays at a predictable rate. So by measuring how much radiocarbon is left in an object such as bone, scientists can estimate how long ago the organism died. However, in the last decade, scientists have discovered that extreme solar storms can affect the amount of radiocarbon absorbed into living organisms, such as trees. This provides researchers with the opportunity to search for extreme solar events not recorded by the history books and to precisely date them. The amount of radiocarbon in the atmosphere varies over time, which can make radiocarbon dating give misleading ages. There have therefore been extensive efforts over the years to calibrate the radiocarbon record to make it more accurate. This means relating it to other material of known age. These might be trees, which can be dated through their growth rings, or stalagmites and corals, which have been dated using other methods. When combined with the science of determining ages from tree rings, the radiocarbon signature of an extreme solar storm can provide a reference point to the exact year. This could help make radiocarbon dating even more accurate. By reviewing the available evidence for these extreme solar storms, we can now try to figure out how often these events occur. The evidence tells us many things about the global carbon cycle, ocean and atmospheric circulation, and the workings of the sun. In 2012, a team led by Fusa Miyake at Nagoya University in Japan discovered that extreme solar storms could produce abrupt changes in the radiocarbon concentrations found within tree rings. Before this, radiocarbon production rates were not thought to vary substantially over short time periods, and so annual measurements of past radiocarbon were unlikely to be of particular interest. They identified the massive spike in radiocarbon production in the atmosphere associated with the AD 774 extreme storm. Other extreme events have since been confirmed to have occurred in AD 993, 660 BC, 5259 BC, and 7176 BC. The most extreme solar storm we have detected in the radiocarbon record took place around 14,370 years ago, towards the end of the last ice age. We do not yet know if these events are simply larger-scale versions of regular solar storms, so-called black swan events, or if they are caused by distinct physical phenomena. As more extreme solar storms are identified from the radiocarbon record, they will add to our knowledge of physical processes occurring in our parent star. One of the biggest threats from a large solar storm is its potential to instantly kill the entire satellite fleet, as well as to bring down power grids. Being able to forecast these events and give advance warning to grid operators is vital. In coming years, the radiocarbon record could well reveal more extreme solar storms. The scientific community is racing to analyze old trees from different regions of the world with the goal of strengthening existing evidence and discovering new extreme solar storms of the past. Enhancing our understanding of these extreme events is not only important for precise radiocarbon dating, but also for understanding processes happening on the Sun and on our own planet. It can also assist us in preparing for the next extreme solar storm. We can't yet forecast when it will happen, but new insights into the past tell us that there will be one sooner or later. A significant revelation: scientists have just found a solution to save Earth. When asteroids hurtle towards Earth in Hollywood films, astronauts often deploy nuclear warheads against them in order to save humanity. And now, scientists have found this strategy could actually help deflect an incoming cosmic impact, not by blowing an asteroid up with a nuke, but by exploding one more than a mile above its surface to shower it with X-ray radiation. As the catastrophic end of the age of dinosaurs about 66 million years ago reveals, cosmic impacts can have disastrous effects for life on Earth. Asteroids aren't just history, they still impact the Earth today. Nathan Moore, a physicist at Sandia National Laboratories in Albuquerque, NM, said, "Apophis, a near-Earth object about the size of the Olympic Stadium, flew by Earth just last week. In 2023, with the Double Asteroid Redirection Test, or DART mission, NASA showed it could potentially deflect a cosmic strike by crashing a spacecraft into the asteroid Dimorphos. Although scientists found the impact successfully altered the orbit of the approximately 160-meter-wide asteroid, the most dangerous asteroids are the size of mountains, and simply colliding a spacecraft against such giants would have minimal effect. Hollywood movies such as Armageddon and Deep Impact have suggested using nukies to shatter incoming asteroids or comets. However, scientists have previously suggested that this might only break an asteroid into multiple fragments, changing a lethal bullet headed toward Earth into a deadly shotgun blast instead. Now, Moore and his colleagues find that nuclear bombs could prevent devastating cosmic impacts if they explode well above the surface of the asteroid. They suggest the X-ray pulse from the outburst could vaporize rock off the asteroid's surface, resulting in a push that could steer a catastrophic strike away from Earth. In a new study, the researchers employed the Z machine at Sandia National Laboratory, the most powerful laboratory source of radiation in the world. It generates powerful electric pulses, magnetic fields, and X-rays to find out how materials react under high pressures and temperatures. The scientists used electrical pulses from the Z machine to generate powerful magnetic fields. These, in turn, compressed argon gas to generate plasma, the same form of matter that makes up lightning and stars. This argon plasma produced the X-ray burst the researchers needed to simulate a similar one from a nuclear explosion. The scientists hung up a pair of targets in a vacuum, each 0.47 inches, 12 millimeters wide, one made of quartz, the other of fused silica. These materials are similar in composition to known asteroids. Moore noted that asteroids come in a variety of compositions, and this new technique can be used to investigate the deflection response of different asteroid materials. Understanding how different asteroid materials vaporize and deflect will be critical for preparing for a planetary defense mission, should the need arise. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
The James Webb Telescope gave us a stunning first look at the depths of our universe.
Since its highly anticipated launch, the James Webb Space Telescope has been a game-changer in astronomy. This technological marvel was designed to explore the cosmos in ways previously unimaginable. With its state-of-the-art instruments and infrared capabilities, James Webb has provided us with clearer views of distant galaxies, star formations, and exoplanets. It has allowed scientists to peer into the universe's most distant corners, unveiling secrets of its early days and shedding light on phenomena we barely understood. However, one of its latest discoveries has sparked a wave of intrigue, concern, and even fear among scientists and enthusiasts alike. The Webb telescope recently detected an object so mysterious and unusual that it has caused many to wonder whether we are truly alone in the universe. Could this discovery point to something extraterrestrial? Could this be a sign that humanity is on the brink of confirming intelligent life beyond Earth? Join us as we dig deep into Webb's shocking discovery and explore what it could mean for the future of astronomy, space exploration, and our understanding of life in the cosmos. First, we have to know that for decades, scientists have worked tirelessly to detect signs of extraterrestrial civilizations, driven by the possibility that humanity is not alone in the universe. The question of whether intelligent life exists beyond Earth has captivated imaginations for centuries, but it wasn't until the mid-20th century that formal scientific efforts to find evidence of extraterrestrial intelligence began. The scientific search for extraterrestrial intelligence, or SETI, emerged in the 1960s when astronomer Frank Drake launched the first modern effort to detect signals from alien civilizations. Drake's experiment, known as Project Ozma, involved scanning nearby stars Epsilon Eridani and Tau Ceti for radio waves. Although no signals were detected, this project marked the beginning of a systematic, scientific approach to seeking extraterrestrial communication. The primary focus of early SETI efforts was radio astronomy, as radio waves can travel vast distances across space without significant interference. Scientists reasoned that if extraterrestrial civilizations existed and were attempting to communicate, they might use radio signals similar to those used by humans. In conjunction with Project Ozma, Drake also formulated the now famous Drake equation, a probabilistic formula designed to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. The equation considers several factors, including the rate of star formation, the fraction of stars that have planetary systems, and the likelihood that intelligent life develops and becomes capable of transmitting detectable signals. While many of the equation's variables remain uncertain, it provides a framework for thinking about the search for extraterrestrial life and continues to guide SETI efforts. Over the decades, SETI has expanded beyond the search for radio signals to include other potential methods for detecting extraterrestrial civilizations. Scientists have recognized that focusing solely on radio waves may limit the chances of success, as advanced extraterrestrial civilizations may not communicate in ways that humans can easily detect. As a result, researchers have begun to explore the concept of technosignatures, which are observable signs of advanced technology that could be created by extraterrestrial civilizations. Technosignatures can take many forms. In addition to radio waves, potential technosignatures might include laser emissions used for communication, large-scale engineering projects like Dyson spheres, or the presence of industrial pollutants in an exoplanet's atmosphere. A Dyson sphere, for example, is a hypothetical megastructure that could be built around a star to capture its energy output. Detecting unusual dimming patterns or excess infrared radiation from a distant star could potentially indicate the presence of such a structure, suggesting an advanced civilization harnessing stellar energy. The search for industrial pollution in exoplanet atmospheres is another exciting avenue for detecting extraterrestrial civilizations. Just as human industrial activity has altered Earth's atmosphere, advanced alien societies might also leave detectable chemical signatures. Certain pollutants, such as chlorofluorocarbons, are unlikely to occur naturally and could serve as a clear indication of technological activity on another world. While radio waves remain a primary focus of SETI, scientists have also begun to explore the possibility that extraterrestrial civilizations might use laser-based communication instead. Lasers offer several advantages over radio waves, including the ability to transmit information over long distances with high precision and minimal signal loss. In fact, some scientists have suggested that lasers could be used for interstellar communication, and the search for these laser signals is often referred to as optical SETI. Optical SETI involves scanning the skies for brief flashes of laser light that could be produced by an extraterrestrial civilization attempting to communicate or send a signal across space. These flashes could be short and intermittent, making them difficult to detect with traditional methods, but new advances in technology and data analysis have improved the chances of finding them. For example, in 2015, researchers detected strange periodic pulses of light coming from a distant star system. Although these signals were later attributed to natural phenomena, they served as a reminder of the potential for optical SETI to play a key role in the search for alien life. As SETI searches grow increasingly complex, scientists are turning to space-based observatories to aid in the detection of potential alien signals. Typically, the historical launch of the James Webb Space Telescope has given scientists an unprecedented new tool for exploring the universe and searching for signs of extraterrestrial life. Unlike its predecessor, the Hubble Space Telescope, the Webb telescope is capable of studying the atmospheres of distant exoplanets in great detail, providing insights into their chemical compositions and potential habitability. By detecting specific chemicals in an exoplanet's atmosphere, such as oxygen, methane, or water vapor, scientists can search for biosignatures, evidence that life may exist on that planet. However, James Webb could also help detect technosignatures by identifying industrial pollutants or other signs of advanced technological activity. Thus, to date, the Supreme has made numerous groundbreaking discoveries. But among those, Webb's most recent detection is perhaps the most perplexing yet. During routine observations of a distant region of space, the telescope picked up an object unlike anything scientists had encountered before. Located in the far reaches of the galaxy, this object is neither a star nor a planet, and its characteristics do not match any known celestial body. Initial scans revealed that the object emitted an unusual and highly structured signal, something not typically associated with natural cosmic phenomena. While space is filled with various types of signals, from radiation bursts to the gravitational waves caused by black hole mergers, this signal appeared to be different. Its regularity and structure hinted at the possibility that it might not be of natural origin. Webb's findings have sent shockwaves through the scientific community, with some speculating that this could be evidence of extraterrestrial technology or even a form of communication from an advanced civilization. If this were the case, it would be the most significant discovery in the history of space exploration, proving once and for all that we are not alone in the universe. However, note that the idea that we are not alone in the universe has fascinated and terrified humans for centuries. From ancient myths to modern science fiction, the concept of extraterrestrial life has been a staple of our cultural imagination. But what would it really mean if we were to discover that intelligent life exists elsewhere in the cosmos? For one, it would challenge everything we thought we knew about life, biology, and the universe itself. The discovery of an advanced alien civilization would prompt us to reevaluate our place in the cosmos. Are we a relatively young species in a galaxy filled with older, more advanced civilizations? Or are we unique, the first to develop technology capable of exploring the universe? The implications extend beyond philosophical questions. A discovery of this magnitude could revolutionize our approach to science, technology, and even international relations. If an advanced civilization were found to exist, it might have technology and knowledge far beyond our current capabilities. This could lead to new advancements in energy, communication, and space travel. On the flip side, such a discovery could also prompt fear and concern. How would we know if these extraterrestrial beings were friendly or hostile? Science fiction has long entertained the idea of hostile aliens. From H.G. Wells' The War of the Worlds to the modern Independence Day, We have imagined scenarios in which extraterrestrial beings arrive on Earth with intentions to dominate or annihilate humanity. But how likely is this? One of the most compelling arguments for hostile extraterrestrial civilizations comes from the concept of evolutionary convergence. Just as life on Earth has evolved through competition, conflict, and survival of the fittest, it's possible that intelligent life elsewhere in the universe has undergone similar evolutionary pressures. A technologically advanced civilization that survived long enough to develop interstellar travel might have done so by becoming highly efficient at conquering resources and subduing potential threats. If these extraterrestrial beings view Earth as a resource-rich planet or humanity as a threat, their arrival could spell disaster. Another argument comes from the dark forest theory, inspired by Liu Cixin's the three-body problem. This theory suggests that any intelligent species in the universe would be wise to remain silent and hidden, because the universe is like a dark forest where every civilization is a hunter. Revealing yourself could invite destruction from a more advanced civilization that sees any other intelligent species as a potential rival. In this context, even peaceful extraterrestrial civilizations might preemptively strike Earth to ensure their own survival. Despite these alarming possibilities, we have yet to encounter any hostile extraterrestrials. One explanation for this is the Great Filter hypothesis, which suggests that there is some monumental challenge or filter that prevents civilizations from reaching the point of interstellar expansion. This filter could be behind us, such as the origin of life or the development of intelligence, or it could lie ahead in our future, in the form of self-destruction or environmental collapse. If the Great Filter lies in the future, it could explain why we haven't seen any signs of advanced alien civilizations. Perhaps most intelligent life destroys itself before it becomes capable of reaching other stars, whether through war, environmental degradation, or uncontrollable technological advances. In this scenario, Earth might be in danger, not from external threats, but from the very nature of technological advancement itself. However, if the Great Filter is behind us and we have already passed it, we might be one of the few, if not the only, intelligent civilizations in the universe. This would make Earth a rare and valuable target for any extraterrestrial beings that are still evolving or expanding. The scarcity of intelligent life could drive these beings to view Earth as a precious resource, one worth conquering or exploiting. To understand whether Earth could be in danger from extraterrestrial beings, we need to consider what makes our planet unique. Earth is abundant in resources, water, a stable atmosphere, and diverse ecosystems. These are the very resources that life depends on, and they may be scarce in the broader universe. If extraterrestrial beings are searching for habitable planets, Earth might be an ideal candidate. Moreover, Earth's biosphere is rich in biodiversity, offering a range of biological materials that could be of interest to extraterrestrial species. For example, they might seek genetic material to enhance their own biology, or they could view Earth's flora and fauna as valuable commodities. Worse still, extraterrestrial beings might see humanity as nothing more than a pest or a competitor for these resources. But if hostile extraterrestrial beings were to invade Earth, would we stand a chance of defending ourselves? The reality is sobering. Any civilization capable of reaching Earth would likely be far more technologically advanced than we are. Their spacecraft would likely surpass anything we have ever conceived, and their weapons might be beyond our comprehension. The vast distances of space require such advanced technology that even detecting an approaching alien civilization could be nearly impossible until it's too late. For comparison, think of the arrival of European explorers in the Americas. The indigenous populations had no defense against the invaders' advanced technology, and the result was catastrophic. Similarly, Earth might be vulnerable to an advanced alien species that views us as little more than an obstacle in their expansion. Some theorists have proposed that we might already be under observation. The idea of a galactic zoo suggests that advanced extraterrestrial civilizations are deliberately avoiding contact with us, either to study us in secret or to wait until we are more technologically mature. However, if these beings are observing us, they might also intervene if they perceive us as a threat to their interests or to the stability of the cosmos. While the prospect of hostile extraterrestrial beings is frightening, it's also worth considering whether Earth itself might pose a danger to them. Earth is teeming with microbial life, some of which could be harmful to extraterrestrial biology. Just as humans brought diseases to indigenous populations during the age of exploration, Earth's pathogens could pose a significant risk to extraterrestrial invaders. Moreover, Earth's atmosphere and environment might not be hospitable to extraterrestrial life. Our atmosphere is rich in oxygen, which could be toxic to other life forms. The gravity, radiation levels, and magnetic field of Earth might also be incompatible with extraterrestrial physiology. In this case, even if hostile beings were to reach Earth, they might find it difficult to survive or thrive here. Should we be sending signals? One of the most controversial aspects of the search for extraterrestrial life is whether we should be sending signals into space. Projects like METI, Messaging Extraterrestrial Intelligence, aim to actively send messages to potential extraterrestrial civilizations, hoping to make contact. However, this approach has been criticized by some scientists who argue that it could be dangerous to reveal our location. If the universe is indeed a dark forest, sending signals into space could be the equivalent of lighting a beacon for potentially hostile civilizations. Even if we are not currently in danger, announcing our presence could invite unwanted attention. The question of whether to remain silent or to reach out to the stars is one of the most pressing ethical dilemmas in the field of astrobiology. If we do encounter extraterrestrial beings, hostile or not, diplomacy might be our best hope for survival. Establishing communication with a completely alien species would be extraordinarily difficult, as their language, thought processes, and motivations could be entirely different from anything we've ever encountered. However, if we can find a way to communicate, diplomacy could help us negotiate peace or cooperation. Science fiction often portrays alien invasions as militaristic, but it's possible that extraterrestrial beings might prefer negotiation to conflict. After all, war is costly and destructive, even for advanced civilizations. If extraterrestrial beings are rational actors, they might seek peaceful solutions that benefit both sides. However, this assumes that we share common values or logic with these beings, which may not be the case. In the end, the question of whether extraterrestrial beings are hostile and whether Earth is in danger remains unresolved. We simply don't know enough about the nature of extraterrestrial life to make definitive predictions. What we do know is that the discovery of intelligent life beyond Earth would be one of the most significant events in human history, reshaping our understanding of the universe and our place within it. The possibility of hostile extraterrestrial beings should not be dismissed lightly, but neither should it lead to fear or panic. The universe is vast and mysterious, and until we have more information, we can only speculate about what lies beyond our planet. What is certain is that humanity must be prepared for all possibilities, both wondrous and terrifying, as we continue our search for life among the stars. In a recent study, scientists have just focused on one of the biggest cosmic mysteries, the dark energy. Almost anything that can be found in space can be removed from it: particles, antiparticles, radiation, electric and magnetic fields, even the curvature of space itself. However, even in completely flat, empty, uncurved space, some forms of energy still remain. The zero-point energy of the quantum fields that pervade all of reality, for instance, as well as dark energy. Are these forms of energy inherent to space itself? And does space depend on dark energy for its very existence? Let's dive in. First, note that there are two ways, fundamentally, to look at the fabric of space itself: from the perspective of quantum fields and from the perspective of Einstein's general relativity. In each of these scenarios, there's an understanding of what space is that are similar, but not identical to one another. There's also, in each of these pictures, a chance for space to have an inherent, non-zero energy to it everywhere, that are again not identical to one another. Finally, there's what we know about our universe from an observational perspective, which is what we base our understanding of dark energy on at present. and which makes us so confident that it does indeed exist. The big question, and I'll even fess up that it's a big unanswered question at this point in time, is how these three different perspectives, the quantum field theory perspective, the general relativity perspective, and the observational perspective, are all related to one another. We can come up with a consistent explanation that ties all three together, but there's no guarantee that's a reflection of what nature is actually doing, rather than a potential limitation in our theoretical understanding of how the universe works. Part of the reason this is such an interesting question is that, fundamentally, we have only a very coarse understanding of dark energy itself, both observationally and theoretically. Here's an outline of the trouble we face. In the 20th century, perhaps the biggest change in our understanding of how the universe works came in the form of the quantum revolution. Reality, as we now understand it, consists of various quanta, particles, antiparticles, and bosons, that propagate through the fabric of space. Everything behaves as a particle when it interacts, even light itself, which is composed of individual packets of energy rather than a continuous wave-like stream. In our universe, as far as we understand it, everything is inherently quantum. This doesn't just apply to the quanta that make up reality as we know it, but also to the fields that permeate all of space. Every particle with a charge, and those fields cannot be extricated from space itself. One of the tremendous realizations of 20th century physics was that these quantum fields continue to persist throughout all of space at all times, even in the absence of any charges that could generate them. This shows up experimentally in various forms, including vacuum polarization birefringence, where empty space itself becomes polarized due to an external magnetic field, the Casimir effect, where two conducting plates placed in a vacuum feel a net force between them due to the excluded virtual modes of the electromagnetic fields, and the Schwinger effect, where a strong electric field can pull particle-antiparticle pairs out of empty space itself and cause them to become real. According to quantum field theory, that's because all of these, quantum fields, always exist throughout all of space and cannot be separated from it, even in the absence of quanta that carry the charges of that field. You've likely seen illustrations of particles popping in and out of existence, or some sort of randomly fluctuating field shown to be inherent to space itself. And while that's certainly an eye-catching interpretation, it isn't necessarily technically correct. Instead, what you should consider as a more accurate picture is that these fields are always there, omnipresently, and that it's only when an external influence comes in, particles, antiparticles, an external field, boundaries, etc., that you're going to observe the effect of the field's presence. However, the fact remains that these fields are always there and cannot be removed or extracted from space in any way. All fields have what's known as a ground state or a lowest energy state that they can occupy. When you take everything else away, including particles, or antiparticles, fields, boundaries, etc., that's what remains. Known as the ground state, the zero-point energy state, the lowest energy state, or simply as the quantum vacuum. This is a property that's inherent to all systems, but one that comes along with an existential difficulty. We have no idea how to calculate what this amount of energy actually is, or what value it ought to take on. In string theory, for example, there are an enormous number of possible vacuum states, at least 10 to the power of 500, and the only way to know which one describes your particular universe is to measure it. Many have tried to calculate, through summing the various Feynman diagrams arising in quantum field theory, to calculate contributions to the quantum vacuum directly. Unfortunately, this yields values for those calculable terms that are roughly a factor of 10 to the power of 120, too large in magnitude. Many posited that, well, these diagrams must all somehow cancel, yielding a zero-point energy that's exactly zero. But there is no support for this idea. It's just a hunch at this point. In summation, quantum field theory tells us there can be a finite, non-zero value for the amount of energy inherent to space, but we haven't advanced our understanding of the universe sufficiently to know what that value ought to be, or how to calculate it. On the other hand, we have our non-quantum theory of gravity, general relativity, that describes our universe exquisitely well in every regime where we've been able to subject it to the critical tests. Instead of a quantum picture of reality, general relativity weaves together space and time into a fabric that curves, ripples, and can expand or contract, depending on the distribution of all the various types of matter and energy that are present within it. Large sources of mass, like galaxies, stars, and black holes, can cause space to curve severely, and that curved space then tells all other forms of matter and energy that exist or propagate within that curved space how they're going to move and evolve in the future. Again, just as in the case of quantum field theory, we can do our best to remove absolutely everything from as large a region of space as we desire, all forms of matter and antimatter, all nearby sources of mass, all types and species of radiation, whatever the unknown dark matter turns out to be, etc. Take it all away, as far away as you care to imagine it, until all you have left is the vast void of empty space itself. You'll find, just as you did previously, that there's one species of energy that, if it turns out to be non-zero, you cannot get rid of from the universe in any way. The cosmological constant, or a form of energy that's inherent to space itself. The cosmological constant has an interesting history. It was first inserted by Einstein into his equation in order to prevent the universe from either expanding or contracting, as without it, any gravitational system of masses would be inherently unstable, doomed to either collapse into a singularity or expand into oblivion. Given the discovery of the expanding universe in the late 1920s, Einstein came to eventually call his introduction of the cosmological constant his greatest blunder, although there's nothing wrong with a universe that possesses a non-zero cosmological constant. There was just no reason to assume it had any value other than zero. But in general relativity, the only way to know something's value is to measure it. There are no dynamics of the theory itself that determine what the value of the cosmological constant is. The theory can only describe how space-time responds to its presence. If there's a positive cosmological constant, it causes space to expand no slower than a specific, positive, relentless rate, even in the absence of all other forms of matter and energy. Similarly, if the cosmological constant is negative, it causes space to contract in exactly the opposing fashion. Unlike all other forms of matter and energy, a cosmological constant's energy density never dilutes or changes. It simply remains constant. In summation, general relativity admits the possibility that there's a positive, non-zero energy that's inherent to and inextricable from the fabric of space itself. But it, too, gives us no way to calculate what the value of that amount of energy is, and no answer to the question of whether it's related to the value of the zero-point energy of space that comes from quantum field theory. Finally, we come face to face with the one thing that all physical theories must inevitably be confronted with: observations of reality itself. We can put the question to the universe of, what are you made of, simply by simultaneously understanding the equations derived from general relativity that govern the expansion of the universe, and then using a variety of measurement probes to see how our universe has actually expanded over cosmic history. Because of the intricate relationship between how space-time curves, expands, and evolves, and the distribution and density of all forms of matter and energy within the universe, making these measurements enables us to know what the universe is made of. Cosmological probes include, but are not limited to, the cosmic microwave background, which is the leftover glow from the Big Bang, a feature known as baryon acoustic oscillations, which gives us a distance scale that expands along with the universe, that describes galaxy-galaxy clustering and is measurable through the large-scale structure of the universe, and distant objects, including quasars and galaxies, that can have some intrinsic property of them measured and known, along with their redshift and distance from us. When we piece together the evidence from a great many lines of evidence, including all three of these, we arrive at an inescapable picture of our universe, one that contains normal matter, radiation, and neutrinos, but where all of that combined makes up only 5% of the total energy in the universe. 27% of the total energy is massive, but not part of the standard model. the mysterious type of energy known as dark matter. The remaining 68%, or most of the universe, according to Nobel laureate Adam Rees, is what we know today as dark energy. Nearly all of our measurements indicate that dark energy behaves as a cosmological constant, although there is some recent data from baryon acoustic oscillations that seems to indicate that dark energy was a constant for most of the universe's history, but may be slightly weakening in recent times, over only the past few billion years. If dark energy evolves in its strength, i.e., in its energy density, over time, then we can't rightfully identify it with either the zero-point energy of space from quantum field theory or with the cosmological constant from general relativity. Only if dark energy is truly a constant, both in space and across cosmic time, do either of these descriptions match up with our understanding of how the universe actually plays out. We have only one instance in cosmic history where the amount of energy inherent to space itself appeared to change. At the end of cosmic inflation, and correspondingly, to the onset of the hot Big Bang. During cosmic inflation, there's strong evidence that the universe was dominated by a period of energy not only being inherent to space, but of being tremendous, of having a value that's many orders of magnitude, at least a factor of Marsh 10 to the power of 100, greater than the value of dark energy today. When inflation comes to an end, the overwhelming majority of that energy gets converted into various quanta, things like matter, antimatter, and radiation. However, somehow, it appears that the end of inflation didn't drive the value that the energy inherent to space possesses, dark energy, down to zero, but rather to a small, positive, but non-zero value, the value we observe it to take on today. Those are the three pieces of information we have about the energy inherent to space itself. We can identify this value with the zero-point energy of space in quantum field theory, the value of the cosmological constant in general relativity, or the strength of dark energy within our observable universe today, which decreased at least once, and tremendously at that, from the much larger value it took on during cosmic inflation. Unfortunately, that's as far as we've been able to come in terms of understanding what's responsible for the energy that appears to be inherent to space. Can this energy somehow be extracted from space after all? And would space continue to exist without it? That would lead to a vacuum decay scenario, which would be catastrophic for life, planets, stars, atoms, and more. But it's not impossible, and it wouldn't cause space to stop existing. Is dark energy evolving or weakening over time? If so, then it isn't something we can identify with either the zero-point energy or the cosmological constant, but rather is some type of field whose value is not fixed, implying that space can exist without it. But if dark energy is truly a constant, then we can justifiably hypothesize that perhaps the quantum vacuum from quantum field theory, the cosmological constant from general relativity, and the observed phenomenon that we see as dark energy are all indeed the same thing, a measure of the inextricable energy that cannot be removed from empty space itself, no matter what you do. Can space exist without it? Unless dark energy turns out to truly evolve, the best answer we can give is, if that's the case, we haven't seen evidence for it yet. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.